Thank you. Hi, everyone, and thank you for joining the Veridise workshop. I'm Andreea Buterchi. I'm the Vice President of Engineering at Veridise. And actually, this is my second time being an Avalanche speaker. So if last time I talked about the DeFi security tools we developed at Veridise, today I will present two automated tools for detecting bugs in ZK circuits. So if you don't have previous experience with ZK in general, don't worry. We designed this workshop in a beginner-friendly way. And of course, if you have questions during the workshop, don't hesitate, interrupt me, and I'm happy to help. All right, so let's get started. So in the last few years, we witnessed emergence of the ZK applications, and now we see these privacy-based contract rollups and also privacy-preserving blockchains. And at Veridise, we've actually audited a couple of these applications, and of course, manually auditing these ZK applications is sometimes a little bit challenging, so we wanted to push the limits of ZK security, and we put a lot of effort into implementing automated security tools for detecting these bugs for the auditors and for the developers in general. And just to give you a big of a background about Veridise, our mission is to bring these security tools to the fingertips of the Web3 developers. And to be able to achieve that, we worked really hard and built this security as a service platform, which provides access to state-of-the-art automatic security tooling. Sorry about that. All right, and again, today we will be talking about, perfect, back online. All right, so today we will be focusing on two automated ZK-related tools, which are ZK Vanguard, a static analyzer, and also PyCus, which is an automated verifier to detect unconstrained ZK circuits. All right, so, I'll just start by giving a brief overview of a ZK circuit workflow. So we basically begin with the source code, which can be encoded in different domain-specific languages, such as Circum or Hello2. And this source code is transformed into two so-called entities, more precisely this witness generator, called P, and the polynomial field equations or the constraints over a very big prime number. And the latter are used to generate two other entities, which are called the prover and the verifier, and they collectively are called a snark, right? So the users use these two entities and implement them in their application to send proofs and verify proofs. All right, so one thing that is worth mentioning is that these circuits are not like the traditional programs that we all know, and they actually contain the computation and the constraints. And so if you cannot yet follow all this information on this slide, we will focus and we will exemplify each of these components on the next slides. All right, so for the language that we'll be using today, for writing these zero-knowledge circuits, we'll use Circum as a DSL. All right, so in general, this zero-knowledge protocols communicate in this way. So there are two entities, the prover and the verifier, and the interaction between them looks like this. So basically, the prover wants to prove to the verifier that they know a secret, But the verifier cannot trust them blindly, so in that case, the prover has to send a proof that they know the secret. And then the verifier is able to verify that information, the proof, and say that, okay, everything is fine, indeed, you know the secret. So there are two important properties of these two entities. More precisely, the prover doesn't have to reveal the secret, so basically this proof that you see on this arrow actually encodes the secret. And also the verifier can always detect false proofs, so the prover cannot treat like the verifier if they don't know the secret. All right, so to see how this concept we talked about previously actually work, I will walk you through this circum basic example, and I will show you, or I will explain to you a few features that are part of this circum domain-specific language. All right, so all the computations in circum are encoded as circuits. So as you can see here in this example, a circuit is a composition of templates. And each of these templates define two elements, which are the witness generator and the constraints. And this witness generation is used to generate that proof that we saw earlier, and the constraints are used by the verifier to check if the proof is indeed correct. All right, and one note is that all these operations are modulo a large prime, so normally when you see A operand B is really A operand B modulo P. And that's why all the signals are between 0 and P minus 1. All right, so we'll continue discussing some of these circum features. And we mentioned previously about the signals, which can be input signals, output signals, or intermediate signals. In general, the input signals, you can consider the input signals as the inputs provided by some users, and the output signals are, the results of the computation. And there are also some intermediate signals which play a role of intermediate variable. All right. What you can see here is the witness generator. So in general, when you see this operand arrow and dash dash, it will only affect the witness generation and the computation, basically. And this operator triple equal will only affect the verifier because this consists of the constraints that will be checked by the verifier. All right, so you can also have signals that are private or public, so you can denote them using this syntax below. Perfect. So we discussed about this very simple circum example, and now to understand how we can split the computation and the constraints part, let's have a look at this execution overflow. So basically here you have the computation, which are assigning values to all the signals, basically compute the values for the signals, and the constraints on the other side, which will be then later be used by the verifier. Awesome. So again, how this works, the user inputs some values, and this computation produces a witness, which is then used to produce proofs, which are inputted to these constraints, and then the verifier says, okay, this looks all right, or your proof is incorrect. And our goal is actually to make the computations and the constraints equivalent, because otherwise the verifier will be able to accept incorrect proofs. So there should be an equivalence between these two. All right, so let me explain a little bit what equivalence means for a ZK circuit. So we saw that this program P takes some input X and output and Y, which is the witness generator. And the constraints take in both the inputs for the program and the output of the program and say, okay, true or false if the proof was verified or not. And to formally, explain what is going on here, for every x and y, p of x equals y, if and only if c of x and y is true. And this means that every input-output of p must satisfy the constraints, and every xy pair which satisfies c must be an input-output pair of p. So this is what we mean by equivalence. And we actually saw in many cases that this property is often violated and results in very severe financial losses. And one of the examples are actually the Tornado Cash hack, where all the tokens could be drained. All right, so next we will be talking about ZK Vanguard and PyCus and discuss some classes of ZK bugs that they can detect. So we will talk about this under constraint circuit, divide by zero, and non-deterministic witness, and we will explain what each of these bugs or classes of bugs mean. All right, so as I initially mentioned, this ZK Vanguard is a static analysis tool. So what you see on this slide is the general workflow of a static analyzer. Basically, we start with the source code. We compile the source code into some analysis representation, basically something that can be used by the analysis phase to figure out if there is indeed a vulnerability in the code base. And the static analyzers actually use some detectors as input. So for instance, we can say that I want to see if there is a divide by zero vulnerability in my code, and then if something is going on in there, it will output a report with all the vulnerabilities found. Okay, so even if this analysis representation is hidden from the user, we will have a look at how it works and how we use it internally to find these vulnerabilities that I mentioned before. All right, so here you see so we use basically some nodes, right, which correspond to the input signals and to the output signals. And we can basically encode the relations between the output and the input based on the assignment operators or the constraint or the equality check on the last line of this code, right? So we can basically encode this assignment between the input and the output with this arrow, and this means that the input signal participates in the output signal. All right, and the next one is this equality check operator, and we denote the relationship between in and out with this dotted line. So basically, this means that the constraint, the input and output signals, constrain each other, which is a very desired property. We'll see why in a while. All right, so there can be also these are not so there is no restriction for the edges between the input and the output. So in fact there can be this equality constraint or this assignment between the input and the output. And there is this special operator with arrow and double equal, which actually is the equivalent for these operations combined. Perfect, so we call this the constraint data flow graph because the data flows from the input to the output, and we added this constraint part because we actually reason about the constraints that are part of the circuit. So based on this representation, like internal representation, let's explore some classes of bugs. So we mentioned previously about these under constraint circuits. And in fact, this type of bug is highly related to the equivalence between the prover and the verifier. And basically, what these under constraint circuits allow is that for a single input X, like we will have distinct output. So there is some undeterministic behavior going on here, which is undesired in most of the cases because the verifier then could accept invalid computations. So we'll have a look at an example that will showcase this under constraint circuit bug. So here on this slide, you can see some method, an adder that takes into binary values and a carry, and it will output if the addition was performed correctly. So basically, so on the right side, you can see the assignment, and for instance, on the first and the third line, we compute that this is the part, the computation part, and what you see with the triple arrow equal are the constraints. So basically, we only check if these output signals are binary. We don't check anything about the addition, which is kind of wrong because we can input to. So we can send a proof that is actually wrong. So basically, we want to add like 1 and 0, and in fact, and add a carry. There is a mistake on the slide. So on the second line, it should be carry assigned to 1 instead of 0. So if we have like a binary value 1 and 0 and a carry 1, it means that 1 plus 0 will be equal to 3, which is not correct, right? Because of the carry. So in fact, because we only check the outputs here, it will mean that we don't check anything about the addition. The addition can be performed incorrectly, and we will be able to trick the verifier to accept incorrect proofs. So here is a depiction of this example. We see that the output constraints are not related to the input. The output signals are not related to the input. We see that dashed line. It's not. So it doesn't connect any input from the output. So it means that these outputs are, in fact, under constraint. They don't depend on the input. So some users could basically send bogus data, and the proof will be accepted, which is not desired. All right, so here we have a divide by 0 example. It's super easy to detect such, such cases. We can, check the data flow in the graph and identify that there is actually a division operation, and we can, like for x, can take 0 as a value, which will trigger a divide by 0 warning. And there is also another bug, which is called non-deterministic witness. Basically, this usually happens when we have conditionals. And in general, so here on the last line of this program, you see a conditional. So basically, the output can take like multiple values, which is not desired. Basically, you can get undeterministic results because of this conditional statement here. All right, so now we can have a look at the demo of ZK Vanguard on our Security as a Service platform. Okay. I recorded a demo of our SaaS platform. So here you can see the interface. We create a new task and upload an archive with the source code, with the circuits. We select the source code for the circuits and upload the archive to our security tool. And then we select the language. We have like multiple tools for Solidity and also for Circum, and we chose Circum. And we also want to dump this this graph for the analyzer, and stare at it for a while just to see how the tool worked internally. And as you can see here, Vanguard outputs a non-deterministic witness detector issue, and it actually indicates where this non-deterministic witness issue happened, more precisely in this signal Y. And we can have a look at this data flow graph that we also saw on the previous slide. This is, just to check how the internal representation looks like. Okay, and the second tool that we'll talk about is PyCus, and PyCus is a verifier that automatically checks whether ZK circuits are under constraint. So it is specialized on the under constraint circuits. So again, it will take like the circuit, and it will output if the circuit is deterministic, meaning that it like the verifier doesn't accept bogus inputs, and it will also trigger a warning if the circuit is under constraint, or it will output unknown because we also set an output. Not an output, we also set a timeout for this tool, and if the tool is not able to find a vulnerability in the given timeout, then it will output unknown. So you basically have to run the program again with a larger timeout. All right, so basically at its core, this PyCus tool, it is using both static analysis and SMTs. And I will just focus briefly on the SMT part. Basically, we saw that this equality constraint can be encoded as a logical formula, right? So if there are two different outputs for the same input, and this logical formula is actually satisfied by our constraint, it means that we found a bug. So PyCus will output under constraint circuit. All right, so as I said, PyCus is using both these techniques. Of course, like this SMT can get stuck because it tries to evaluate as many inputs as possible, and when it gets stuck at some point, it is collecting some information from the static analysis phase, and these two components of these tools are communicating in an interactive loop such that they help each other to find the result faster. All right, so I mentioned these things already. You can check out our PLDI paper if you want to see which results we obtained for PyCus. This is a work in collaboration with some of our partners, ZeroXPark and ZConduit, and just a few, just to exemplify this, how this tool works. Here is an example which basically has a vulnerability because in this for loop, we don't loop like until the very last element, and we will loop until the previous element. And when we instantiate this example with n equals to 3, we will notice that this the last output signal will be under constraint. So basically, the users can pass any value for this output too. So let's have a look at this PyCus demo on SAS. Again, it works in the same manner as ZK Vanguard. Basically, we upload the archive with the source code, with the circuits. We indicate the path to the source code, and then we select PyCus, and it will run the analysis on the bug example because we will also check the fixed example to see what is the output of PyCus in that case. So as you can see here, the output looks like this. PyCus indicates that there are two possible inputs. There is one input that will generate two possible outputs, which translates to undeterministic behavior. So now we upload the same code, but the fixed version of it, and we'll see that PyCus will say that everything is all right with respect to this unconstrained property. Perfect. So just a few takeaways. These hidden ZK bugs could lead to severe financial consequences, and we at Veridise work on automating this process of uncovering ZK bugs, and we provide the developers with access to our SaaS platform to just try these tools and use them for their products during the development process. And of course, ZK Vanguard and PyCus employ static analysis and SMT reasoning techniques to secure ZK-based products. So thank you very much. If you have questions, I'm happy to address them. Of course, if you are interested in the audit we performed in the past for this ZK, for all these ZK clients, please check out our webpage by scanning this QR code. Thank you.